Hello, everyone. Thank you for joining us today. My name is Jay Singh, and I will be your host for this NASA Ames Technology Transfer Program webinar on the various cutting-edge technologies that come out of NASA Ames Research Center here in Mountain View, California. The webinar will be structured in a lightning talk format, so the presenters will have 10 minutes to present their technologies and then 5 minutes for Q&A. Before we get started, I just wanted to mention that the Technology Transfer Program has over 1,000 patented technologies across the entire agency and 100 different technologies at Ames available for the public to license. I'd also like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the Q&A box. We'll answer them during the Q&A session at the end of each presentation. So at this point, I'm going to turn it over to our first presenter, Priyank. Priyank, take it away.
Thanks, Jay. Hi, everyone. I'm just trying to share the screen. Can you guys see the screen?
Yes, looks great.
Okay. So title of today's presentation from my side is Method and System for Wind Optimal Airspeed Target and Airspeed Predictions at Waypoints for Use in Flight Management System, also known as FMS. So here's the outline of today's presentation. I'll introduce you guys to Flight Management System, also known as FMS, and for performance and guidance functionalities of FMS that's relevant to this research, followed by different speed modes that's used in FMS, and quick look at results of our research at NASA Ames Research Center on wind optimal airspeed, followed by claim or US patent that we filed, and then various applications of this technology. So as we know, flight management system is a specialized onboard avionics systems which automates a wide variety of in-flight tasks that reduces not only pilot workload but increases situational awareness of these pilots. FMS also provides different functions in real-time, event-based, and periodically, like performance optimization, which involves optimal altitude, optimal speed, step climb, and stuff like that, flight planning, trajectory prediction, lateral and vertical guidance, navigation, data link, and interface with primary flight display and navigation display. So the highlighted text over here shows the functions that are directly related to our technology. Okay. Yeah, so sorry about that. So as performance and guidance are directly related to our research, so I would just quickly go through them. As you know, FMS has two subsystems, aircraft performance and guidance, which are critical to flight performance. And when we talk about aircraft performance, it's about finding optimal speeds for different flight phases, finding aircraft performance limits like max operating velocity, max operating Mach, maximum altitude, minimum airspeed, placard speeds. And when it comes to prediction, trajectory prediction, it's about finding fuel and energy consumed or remaining at various waypoints, and also estimated times of arrival to various waypoints in active flight plan. When it comes to guidance, lateral and vertical, FMS helps in providing target airspeeds, altitude, and heading to flight control system. Now let us focus on speed modes. So typically FMS has 4 or 5 speed modes that pilot can select based on the mission. Like for example, long range cruise is for minimizing fuel consumed for a given range. Econ is all about cost index. Max endurance is about maximizing loitering time. And required time of arrival is about reaching a waypoint at dot. So depending upon pre-selected airspeed mode, FMS predicts airspeed, estimated time of arrival, fuel consumed at various waypoints in the active flight plan. And it also uses this information to target airspeed based on the level of automation, whether it's fully coupled with automatic flight control system or mode control panel, or pilot takes it as advisory and targets on its own. So our research, simulation-based research at NASA Ames using a multi-rotor aircraft showed that flying wind optimal airspeed compared to best range airspeed in headwind conditions had an energy consumption reduction up to 7.5% and flight duration reduction up to 28%. On the other hand, in tailwind conditions, we observed energy consumption reduction up to 2% at a cost of slight increase in flight duration. We also observed that flying at wind optimal airspeed has lower variability and higher predictability in terms of energy consumption and battery usage, even under wind uncertainty where you can't predict wind accurately. So in our claim, which is still in pending application state, so what we are saying is wind optimal airspeed could be a new speed mode in the FMS, and it could be created by either OEM or avionics companies based on the recipe that's in our patent. So this lookup table, wind optimal airspeed lookup table, as described in our patent, can be incorporated in flight management systems using RTCA DO 200 process so that FMS can predict as well as target wind optimal airspeed in real time. So not only FMS, we observed that this technology could be used in electronic flight bag. Also, when it comes to urban air mobility or advanced air mobility, provider of services, fleet operators can use wind optimal airspeed to predict their flight plan trajectory, which is more energy efficient compared to other speed modes. And given the low specific energy density of today's technology of lithium ion polymer batteries, this kind of speed modes would be more accurate and efficient as well. I guess that's it from my side for today. Thank you.
Thank you so much. That was very interesting. So we have a question in the chat. Does this tool predict optimizations in future time? For example, if models predict headwinds will develop closer to the destination, can you speed up to arrive before the headwinds?
Yeah, definitely. So in our patent, you'll observe how to blend forecast versus and sensed wind so that you can take care of all these uncertainties.
Oh, awesome. That's great. And I think you touched on this just briefly, but how does this differ from what's on the market right now? How is this better?
Yeah, so the key aspect is, Jay, like this kind of speed mode takes care of wind with like it not only takes care of aircraft type, mass, mission, and all, but it's highly sensitive to wind. So the predictions that it does using wind optimal airspeed for an aircraft is more efficient. So it would definitely help operators in reducing fuel consumption or battery usage. So
Oh, interesting.
in short, I would say it's more efficient than other speed modes.
Got it. Very interesting. And so you were saying it was with batteries, so this could be used on the future of electric vehicles or
Yes,
electric planes. Okay, got it.
definitely.
We'll just wait on any other questions before we move on. So I guess while we wait for any other questions, what was kind of the reason to create this? Was it something that your team was like, hey, this is something that's needed out there? in the world, or was it for a NASA mission?
Yes, exactly. So we were studying trajectory optimization of different vehicles given the low specific energy density of lithium ion polymer batteries. And then while researching, we observed this kind of speed mode. And then based on our backgrounds, we realized this could be transferred into a technology for a feature enhancement kind of thing for existing flight management systems.
Oh, fantastic. I think we don't have any more questions. I guess was one last one. Who do you think the most likely customer could be? Aircraft builder, um, Department of Defense, FAA, whoever it might be. Who do you think the most likely customer
So
would be?
definitely aircraft manufacturers, avionics companies that build FMS and other avionics device. But in this new world of urban air mobility and drones, I think even fleet operators
Oh,
for
great.
for better planning.
Yeah. Awesome. Thank you. Appreciate it.
Thank you, Jay.
Yeah.
Thanks a lot.
So next up, we have Jessica. Jessica, please take it away.
Yeah, thank you so much. Okay. My name is Jessica Koehne. I'm here from NASA Ames. I'm going to talk to you today about an innovation put together by myself, Morgan Anderson, and Milton Cordero. And going to talk to you about the development of an electrochemical sensor based on enzyme-linked immunosorbent assay. Let's go to the next slide. All right. Okay, so an enzyme-linked immunosorbent assay, if you're not familiar with it, it's also commonly referred to ELISA, so I'll just refer to it as ELISA from here on out. It's generally performed in a 96 well plate, where the bottom of the plate you will have a capture antibody that will specifically bind a target antigen, something you're trying to detect. Then you add a secondary antibody on top of that. And on that secondary antibody, which we also call the detection antibody, you have an enzyme attached. That enzyme will then drive a reaction to a product that you can measure. The example that we've given here is a colored product. So this is oftentimes a colorimetric assay, but it can also be electrochemical. Let's go to the next slide. Okay, so this is what we've developed. We've developed a magnetic electrochemical ELISA. And we have some of the same components as you saw on the more generic ELISA, but let me just kind of walk you through it so you can understand the differences here. First, instead of just having an antibody on the bottom of a well plate, we have an antibody that is modified on the outside of a paramagnetic bead. And this paramagnetic bead then can interface directly with a detector, in our case, a gold electrode, through the use of a permanent magnet that we can put in contact with the bottom of that electrode and draw the paramagnetic bead close to that electrode surface. So as I mentioned, we have an antibody that's on top of the paramagnetic bead. It then binds, we have here shown a viral particle. This was developed around the pandemic, but this can be an antigen that specifically binds to that primary antibody. And then our secondary antibody, or detection antibody, we put in as this detection construct, which is based on a microbead that has a lot of these secondary antibodies attached. The detection construct also contains a enzyme, and that enzyme that we use here is HRP that will turn over a reaction of a reporter. And let's go to the next slide because I show the reporter. The reporter in our case is this molecule TMB. So the HRP enzyme turns over TMB to TMBD, but when we pull this whole reaction close to this electrode surface, and this is by employing that permanent magnet, and utilizing the magnetic bead, we are able to regenerate the TMB. And because everything is in close proximity, we're able to cycle this reaction over and over again. And this is what we're calling in this slide a positive feedback. And so the example data set that I'm showing you on the right-hand side, oops, sorry, let's go back. Okay. When we say no feedback, this is essentially like a detection experiment where we just have these things floating in solution and we don't employ the magnet. But as we employ the permanent magnet in contact with the gold electrode, we get this big bump in signal from this cycling of this TMB-TMBD reaction. So let's go to the next slide. Okay, so we started out measuring this reaction in a stagnant liquid cell, and we used a variety of different electrodes. I mentioned that the electrode is gold, and so these electrodes range from just a gold film to kind of more complex structures like what I'm showing you here on the left-hand side. And this is a microelectrode array of these kind of dots of gold. The electrochemical cell is shown on the right-hand side. This was a kind of a quick and dirty prototype that we just utilized for laboratory analysis. And the piece of plastic, the white plastic up at the top, that is where the liquid cell actually is. The sensor electrode is kind of sandwiched between that and the black plastic down below. You can see there's a solenoid underneath that is going to actuate a magnet up and down to make our measurement. And let's go to the next slide and see what this data looks like. Okay, so to begin with, to kind of understand how this whole system worked, we created what we called then a model bead. And so this model bead was a paramagnetic bead. It contained the HRP, so this is the enzyme that would drive that reaction of TMB and TMBD. We first performed a measurement where we introduced the TMB into solution, but we don't have any beads, and so this is kind of a blank, and you can see we don't observe any current here. Now let's advance the slide. Okay, now we add the beads, but we don't employ the magnet. So this is the case where you just have this reaction occurring in solution. It's all going to be diffusion based to get that reactant close to the electrode surface to see a change in current. And now let's advance the slide once more. Okay, so this is where we have the paramagnetic bead, and we employ the magnet at this timeline, which we've designated by the red dotted line. And so what you see is as the magnet is employed, draws the paramagnetic bead down to the electrode surface, and we see this drastic increase in the magnitude of signal that we measure. So let's go to the next slide. All right, so then we actually calibrated the sensor, and the baseline here we're showing this is just it in solution, and then the orange is with the magnet employed, and we got very, very low limits of detection down to 99 zeptomole this is the model bead construct. Let's go to the next slide. Okay, I mentioned we did a lot of different comparisons with different electrode geometries. Maybe what I want to show you here is on the right-hand side. This is looking at a limit of detection. So you actually want these bars to be very low. And what we're looking at is when the magnet is employed, it's lower than the baseline, which is the blue. But we also compared it to an optical approach. TMB is actually a colorimetric indicator as well. And what you can see is our electrochemical approach is outperforming the optical approach. In addition, employing the magnetic field on this assay is drastically improving the limit of detection as well. So let's go to the next slide. Let's skip this, go one more. Okay, so then we performed the assay now not with the model bead, but we gave it 2 antibodies that were specific for a target antigen, and we performed a detection experiment with a positive experiment was with the antigen that would bind the two antibodies, and the negative control was a different type of antigen that did not bind. And so we now are seeing the data set as it comes out with binding of a target antigen. And what we've seen here in these studies is that we're getting, our best case was a 35, roughly 35 times enhancement in sensitivity after we employ the magnet. Let's go to the next slide. So we then started working on this. We just wanted to kind of do a proof of concept that this could work for protein detection as well as DNA or RNA detection. And so that's what's shown here. So our assay is very similar, but instead of having an antibody as a probe, we turn to an oligonucleotide probe on both the immobilization and detection constructs. And that then can bind to a target oligo. We can be looking at DNA, we can be looking at microRNA. Let's go to the next slide. So this is some of our kind of preliminary data that we took on just looking at DNA detection, again, in what we're calling the stagnant cell. And so we introduced oligo targets of different concentrations. And there's still work to be done here, but we're seeing in this data set that we're detecting down to 16 picomole of DNA target for this experiment. Let's move to the next slide. So for where we're taking this in the future with NASA, we need to kind of enclose this system to make it autonomous. And so we're designing a liquid cell around it. And that's what's shown here. So it's going to be a fully closed system instead of the open stagnant cell. Let's go to the next slide. And this is looking at DNA detection in the flow cell. And so again, what you're seeing is we have a control, a non-complementary target. Well, maybe what I'll tell you first is our two blanks, which you can see is they're overlapping blue and green lines, are not seeing a change in signal. But our complementary and non-complementary targets, we see a little bit of a change with the non-complementary and a drastic change with the complementary binding of that target. That's the red curve there. And then I think we got one more slide of data. Let's advance. Yeah, so we did this study again in the flow cell, but looking at DNA and then also looking at microRNA as the analyte detected. And this is some of the preliminary data that came from that. The RNA in particular was 2 nanomolar concentration of a complementary microRNA with 2 non-complementary strands as well. And so, as I said, this is still preliminary, but this gives you an idea of what the technology what has been developed and where this can go. And then next slide is just kind of my end slide here. For more information, this is where you can find our technology. So I'd be happy to take any questions.
That was great. Thank you so much. Very informative. So we have one question right now. Anyone else has any more questions, please feel free to put them in the chat. How does this compare to luminescent and fluorescent assay WRT sensitivity and dynamic range?
Yeah, I mean, I believe our sensitivity is rivaling fluorescence at the moment, but fluorescence can also be a very, very sensitive technique. I hesitate to kind of answer this specifically at the moment, just because we haven't done the direct comparison with same assays like we have done on the optical colorimetric approach. So but I would just kind of say what our numbers are that we've measured so far, down to a zeptomole concentration of the model constructs. But it is looking like a very, very sensitive technique, as is a fluorescence approach.
And then we just had a comment. Somebody said this is amazing, thinking this could be applied in biotech. perhaps with residual DNA test methods in cell therapy vector technology. Do you have any thoughts on that?
Yeah, I mean, we're really we're very excited about this as well. I'll just say that. And right now within NASA, I can see a lot of course, potential, in the commercial side as well. We're very interested in using this again for human health diagnostics for the astronaut crew. We're looking at scenarios where outside of that also in situations, basically situations where we would expect very, very low concentration of target analyte. So we're just got into this. We're very excited. Wrote the patent. We're happy to share this. But yeah, we're continuing to work on this as well.
And then we have one last question. What about dynamic range, 10 to the 6?
Yeah, we have some thoughts on that. I will say this system is not probably sufficiently characterized for dynamic range at this point. One thing that we have thought about is that, especially our system as it's designed right now with TMB as the reporter. TMB is a colorimetric indicator. So there's the potential actually to use the colorimetric as well as the electrochemical to expand that dynamic range. And this is just kind of an idea that we've been floating around, but it's so I don't have a very good answer for you on that right now. We're definitely tuned for very, very low limits of detection, but I think there's potential to expand that dynamic range.
Great, thank you. I appreciate the presentation. It was very informative. Next up, we have Guru. Guru, take it away.
Can I start now?
Yes, good to go.
Okay. Yeah, my name is Guruswamy. I'll be talking about active turbulence suppression system for electric vertical takeoff landing type air taxis. Next slide, please. So the background, most of you already familiar with the air taxis. They're coming to reality. And this is a brief background about air taxis. Electric air taxis are becoming a viable option to helicopter for several advantages. And among the vertical takeoff landing configurations built with multiple pushing and lifting propellers are more popular. They don't need runways, and even in the small parking lots they can land. But these configurations are susceptible for turbulence and burst strikes because they're a lot lighter, and also they fly low altitude. Presence of buildings, there'll be a lot of disturbance and also atmospheric turbulence compared to aircrafts. Typically, Dutch roll type of oscillation can occur. Even it occurred for a regular aircraft recently, one which was landing in, I believe, in Oakland Airport. It went through wild Dutch roll oscillations. So, but typically for the aircrafts, they do have the vertical tail configuration to control that kind of oscillations. But to add that for the air taxis is going to make it heavy, because keeping it light is very important so that, they can accommodate more passengers. So it's not very practical to use vertical tail, rudder type of configurations. And also the current methods to use the control system, they're all based on the frequency domain approach, and they can use Lookup tables and linear aerodynamics, highly simplified aerodynamics. But given the complexities of the current air taxis, they will not be adequate to design. So that's one of the things that we'll be addressing in this particular research. This particular invention presents a procedure to suppress the oscillations using the existing propellers. Next slide, please. So main objective of this work is to develop a procedure. This is not a kind of developing an instrumentation. This is just a procedure to generate accurate database to design the active control system based on using the existing propellers to suppress oscillations. So the approach we have taken is, first we need to identify a kind of a very high quality, very accurate flow simulation module because of the flow complexities. That's one of the tasks to do. And in this one, like, there are several, instabilities can happen, but we have taken a typical, like, Dutch roll type of oscillations, which to kind of demonstrate the whole technology. And mainly, like, we're going to present a feedback type of simulation process to design the system for the control oscillations, and kind of demonstrate for a typical VTOL how this technology works. Next slide, please. The typical instability scenario that, the pilot recognizes instability either from instrumentation or by feeling, and once it kind of occurs, the triggers the instrumentation that identifies which motion is predominantly excited, and turns on the control system that is pre-designed to suppress that oscillation. As again, example is the Dutch roll oscillations, which is a kind of uncontrolled roll yard type of motions. In this one, like if it is predominantly a roll motion, like the lifting propellers will be triggered. If it's predominantly like the yaw motion, pushing propellers will be. This is kind of a system that need to be designed. And as I said, this is a kind of involves a lot of flow complexities. So because of the multiple propellers and also like the interactions that with like wings, so that needs can use of a very high fidelity kind of a flow simulation software. And in this one, like, we are using code called Overflow, which is a well-established code developed at NASA. And also, in order to, like, this approach is not to kind of, develop an instrumentation. This is a procedure to generate a database that will be available, like, to design the control systems. For that one, we need a lot of simulations. So that needs a supercomputing and codes which run very well on the supercomputers such as Overflow. The next slide, please. As I said, the flow solver is very important in this process to select and Overflow. This is a brief background of Overflow, which is a code that's been developed for last 4 to 5 decades by several, and it is actively supported by several NASA projects, which is actually used for rotorcraft and also, for air taxis and several other configurations. It is well validated, and there's active users group, and also there's a help. And that's the reason I selected this particular code. And it's available for US companies with, of course, it has to be US citizens and permanent residents. And main thing is it runs very efficiently on the supercomputers, like, all the parallel computers. This is one of the examples I showed at the bottom. This is a simulation done by another group for the quadcopter. Like here you could see that the flow complexities. This requires thousands of hours of simulation with very large grids, but the Overflow code is kind of well kind of designed to handle that kind of situation, and many people are using that code. Next slide, please. This is, as I said, like, this whole approach is to kind of create a database to kind of design use for the active control system. And this is a flow chart. I'm not going to go into details. Mainly, like, in summary, what it will be doing is like, so once we set up the grid systems, and that's kind of a lot of work there, but that's kind of described in papers I'll be referring. Once it is all set up, then we have developed the modules to kind of do the simulation of coupling the flows with the stability equations, and they're all kind of built in to the to this process. So once we have that one, so we'll introduce a possible disturbances. It could be due to a gust, or bird heat, or a presence of a tower, because if the air taxi flies very close to the tower, there'll be interactions, flow interactions with the tower, and that could also cause a disturbance. So if the instability occurs, we find the predominant motion. For example, in the Dutch roll, it could be a yaw motion, or it could be a roll motion, and activate the related propellers, and keep activating till they they get suppressed to within the limits, and once it is it is well suppressed, so deactivate the propellers and store the data. This is a data that they can use it for designing the control systems, and like that, you can go back and simulate for all possible scenarios of disturbance. Next slide, please. So in this, these are the typical VTOL configurations. There are several, different versions are available. This is just an example. The one in the top is with the vertical tail configuration. That was one of the configurations that proposed. But in the bottom figure is the one that I've kind of put together to demonstrate this technology. This doesn't have the vertical tail. It's got only 8 lifting propellers and also 1 pushing propellers. Mainly this configuration was selected to demonstrate a Dutch roll type of suppression of that kind of oscillations. And in this, the lifting propellers 1 and 8 and 4 and 5, the outboard, they are the one who are kind of get active to suppress the oscillations. Next slide, please. This is kind of details about the Dutch roll oscillations and equations. I do have a paper which kind of mentioned at the bottom of the slide, which gives the details. Is AAW detailed paper. The Dutch roll oscillation, series of out of phase turns, where the aircraft rolls in one direction and yaws in the other direction. You could see in the figure on the right hand side. Main thing is right now there are a lot of stability equations and also a lot of methods to kind of understand this phenomenon and also suppress, but they're all based on highly simplified aerodynamic equations like lifting line theories or lookup tables. But given the current complexities of the new aircrafts and particularly the air taxis, that kind of we need a lot more sophisticated or a physics-based model, which is that means we need to use CFD. But once you use a CFD, the challenge is to couple its stability equations, because the current stability equations, they kind of use the aerodynamics as a function of displacements and motions. Therefore, they are kind of highly simplified, but that's not possible. So you need to come out with a very good coupling mechanism of coupling the stability equations with the CFD. There's a work which has been going on at NASA, all the NASA centers, particularly NASA Ames is a lead center in that one. For last couple of 4 to 5 decades, we have developed several methods to kind of couple the CFD with Euro-elastic equations. And this is one of the examples. For example, the Dutch roll equations are quite complex, and this one of the first order type of equation that has been developed by Banner and Cole of NASA. In this one, that whole Dutch roll, like phenomena is represented by a single variable, like side slip beta, and so we kind of so this is the one kind of was possible to kind of couple with the CFD as a first effort. And here the main challenge is to kind of compute the quantities like n beta and L beta. So they are the rate of changes of the roll and yaw moments with complex aerodynamics, so that's the one which code overflow can generate very efficiently. Once you have these quantities, and we can go back and compute the roll and yaw rates, and compute the displacements which can be input to the control systems. And there is a paper on this one, which I have mentioned at the bottom, which gives more details. Next slide, please. Next. So this is the active control strategy. And during the cruise, it's assumed that the lifting propellers are like a stationary, or they'll be with a very low speed, so that there'll be less inertia in case need to activate. And as I mentioned, the outboard propellers they are the one who get activated. That means when wing is going downward motion, the propellers, like the outboard propellers, corresponding outboard propellers get activated. I'm going to show that in this. But for this one, we need a lot of information, what speed they need to kind of be activated. And in this, we kind of come out the relation of relating the, for example, the roll angle of attack with the RPM, the speed. These details are available in the paper, and how they are computed with overflow code, because the computations are quite complex, and also we need to kind of simulate the change, the variation of the speed, that is rotating speed. All this is explained in the paper. So next slide, please. So this is a demonstration of the suppression of the Dutch roll oscillations. On the left-hand side, you see the figure which shows the plots of the beta, that is the side slip from the equation I showed earlier. And disturbance has started due to some reason, and it starts growing. If you see in the and if you see the dotted line, that's what shows if there's no control system, the beta, both beta along with that one in the roll angle, because this is a coupled phenomena, because the energy starts exchanging between the yaw motion and the roll motion. So here I'm just showing for the side slip, the yaw motion. But once kind of the roll angle, or yaw angle has kind of reached some kind of undesirable level, then the control system can get activated. That means the propellers gets activated. The one that is supposed to be get activated, that means the outboard propellers. And once they get activated, it starts suppressing the oscillations. You could see that change in the RPM. In the beginning, it'll be high speed. As it gets suppressed, the RPM keeps reducing. Can you go to the next slide, please? Yeah. You could see that once the wing that goes down, the propellers get kind of gets activated, and the speed of the propellers depends on the amount of roll angle. this is also you could see the flow complexities involved, like with a lot of interactions take place. This kind of simulation is quite challenging numerically, and that's where the codes like overflow plays a very big role, because it's kind of well designed to handle this kind of motions. Even it can add a lot more complexities in the configuration. The next slide, please. So, I would like to make some concluding comments. A procedure to actively suppress the oscillations by using the existing propellers. That means, there's no new hardware is required. Whatever is existing, the pushing or or the lifting propellers is developed for VTOL type of air taxis. This work, this development includes a numerical procedure to generate the calibration data to design the feedback active suppressing system, as I demonstrated. And as I mentioned, it uses high fidelity flow solver, and also coupling that with stability equations. And the results are demonstrated. This is a demonstration for Dutch roll. The technology can be used for to separate other type of oscillations also. That concludes my talk, please. Thank you.
Great, thank you so much. We have time for just a couple questions. So yeah, I was wondering, how is this better than what's on the market right now?
I don't know what exactly they may be using it, because that probably they don't disclose it. And so main thing, this will because some of the configurations they are trying to use control systems like the vertical tail and horizontal tail of configurations. Mainly this particular work was initiated to to avoid using that kind of configuration. This was started about 3 years back. That time the air taxis were very new, and so so essentially this presents whatever system they have it, they can use it to control, and also another thing, using the high fidelity equations is the one this kind of offers. So when they have the more complex systems, they can understand a lot better. So
Got it. Thank you. And we just have one last question. Is this used for military operations that you know of? I guess you wouldn't know, right? Because the military one is kind of similar to the corporation thing that you're saying.
yeah,
Yeah, that makes
because
sense.
there's not much data is available, this kind of so we don't know what exactly they use it, how but the only thing that, we know is they still use the lookup tables and that kind of data for the aerodynamics, but the it may not be adequate to simulate during for example atmospheric turbulence. So that so this particular method development would gives that kind of capability.
Yeah. Great. Thank you so much. I appreciate it. It was very interesting. And next up, we have Evan. Evan, take it away.
Okie dokie. I'm going to share my screen. Full screen. All right. Do we see that?
There you go.
Okay, sounds good. Okay, so hi everybody. I'm Evan, and today we're going to look at vision-based approach and landing system. And so this is similar applications, just like we heard from Guru for like advanced air mobility or like flying cars. Okay, so we'll start with the high-level quad chart. We'll start with our technology overview and why we created this. So advanced air mobility or AAM, we need accurate and autonomous approach and landing systems. But there are some challenges, of course. So if you're in an urban environment, there's a lot of tall buildings, your GPS signal is not going to be that good. You're going to have these narrow glide slope and localizer beams, and we'll look at some pictures about what I mean about this later on. But these beams are also very narrow, and so you're not going to have a lot of alternative incoming angles as you want to come in for landing. And again, I'll show you a picture about this a little bit later. For applications, we have a PowerPoint slide from the FAA and the national campaign, and they had some guidelines about what they expect for these approach landing profiles. So we're going to use this for our research. So on the top right, here's a high-level block diagram of our vision-based approach and landing system. So I'll start from the left side. We take a picture with our camera, could be running at say 30 frames per second. We generate some images. We run our feature detection, estimation, and correspondence part. And then after that, we run a numerical solution with a algorithm called coplanar pose from orthography and scaling with iterations, or composite for short. And this doesn't run all the time. It depends if you get at least 4 coplanar points detected or not. So we want this to run as fast as possible. So typically we've seen it run from anywhere between 10 to 20 hertz. And composite will output the estimated aircraft position and attitude or orientation. Then we feed that into an extended common filter, which will be running at 100 hertz. That'll combine the information from composite and then onboard IMU running at 100 hertz. And the IMU will give us the acceleration and body rates. And then we'll combine all this and output our estimated state position, velocity, and orientation. So what are some benefits? So if we have this working pretty well, we don't need to rely on GPS. We have an alternative position, navigation, and timing, or APNT solution. And this is going to be a safe and accurate method for approach and landing for advanced air mobility. We'll also find some technological gaps and some hardware gaps in the current technology we have in AAM. But overall, this is going to increase autonomy and efficiency. You won't need a pilot to do all the landing for you. You can save some payload capacity. And this will pave the way for new solutions for APNT, as well as AAM operations during approach and landing. So some more background details. So again, we're going to look at the landing lights and then some traditional current landing systems. And then if you're curious about the algorithm, we can go back to that a little bit later. So that's an appendix slide. Okay, so let's look more into landing lights visual aids. So there's no active FAA vertiport document. They canceled this in 2010. So our next best option is to look at similar documents for some requirements and standards. So we have the heliport design document. So this has some landing lights for us to use. There's also a FAA vertiport design engineering brief. This has some interim guidance. It's not super official, but it gives us some insight into what to expect for our landing light configuration at top of vertiports. So in a traditional and current landing system, you have, let's say you're a flying car thing and it's going to land at a vertiport, and your localizer is that blue triangle there. So if you have a traditional glide slope localizer, well, this might work in simple, straightforward cases without buildings or any obstacles in your way. But if you have these narrow beams, you're not going to have a lot of alternative incoming angles for approach and landing. It's going to be very difficult to maintain a consistent glide path around the buildings. Okay, so we're going to look at the highlights of 3 papers that use this valve system. So we'll start with our 2022 paper. So modifying that slide I showed at the beginning, that quad chart, we can modify the FAA and national campaign slide. This can give us some concrete locations for the approach and landing. And composite requires at least 4 coplanar plates. And the landing lights are going to gradually be out of field of view. It's going to be behind us. And so this paper, we just look at the glide slope descent from point A to B. So we ignore C, D, and H. So overall, the position estimation results are pretty accurate. The red and black lines, they align very nicely. There's some small fluctuations in east there, but overall the scale is very small, so it's pretty good. Our velocity estimation is also pretty good. We have some small fluctuations in the beginning as the EKF is still converging. For our orientation, there's some large spikes and fluctuations in these Euler angle estimations, but they're very small. That's pretty good. But our glide slope error does diverge over time because it accumulates small errors over time. Our localizer error has small fluctuations, but it has a generally pretty accurate lateral or east estimations from our composite measurements. So the next paper from 2023, our simulated vision-based approach landing system for advanced air mobility. We'll look at some highlights. So we created a simulated AM trajectory from Oakland to San Francisco. So here's a Google Earth picture of that last portion in San Francisco. We carefully designed a waypoint-based trajectory by placing waypoints around and between buildings in San Francisco to avoid collisions, of course, with the buildings. But as you can see, it's a very cluttered urban environment, so it's geometrically very difficult to maintain a constant glide path like we saw in that earlier slide. So consequently, we end up with this curved trajectory. So here's a screenshot of the vertiport at San Francisco. Specifically, this is at top of the 5th emission garage. And World Editor is the software that we use to create and modify airports and scenery. And then you can send that modified scenery over to X-Plane. And X-Plane is a flight simulator that acts as a visualization tool for rendering our simulations. If we were to zoom in here on this red box, we can see our simulated vertiport with helipad lights, landing lights based on the FAA Heliport Design Advisory Circular that we showed earlier. So here's a short video that shows, it's not playing for some reason. It worked earlier. Okay, I'm not sure why. Okay, there we go. So here's a short video that shows the last portion of the landing at 5th Mission Garage in San Francisco in our simulation. So we simulated an AM quad aircraft model, and it has this waypoint-based controller, so it's why it kind of has these bobbing around effects. So we usually have at least 4 detections as we're doing our approach and landing, and this gives us several composite measurements. So this is going to give us many correction steps in our EKF, which ultimately will lead to accurate state estimation. So overall, we have pretty accurate position estimation. There's that staircase-like descent. If you look at the U subplot at the bottom there, this again is because the quad model has this waypoint-based controller. And we also got some accurate velocity estimations with some minor errors. And then if we look at orientation, it's pretty good. We have some small offsets or fluctuations. But overall, we have sub-meter position accuracies, so we do beat GPS, assuming though we can get consistent composite measurements. Now, so our airborne navigation solution, the red line there, is more accurate than our ground-based distributed camera solution because we have in situ onboard measurements with the IMU from the aircraft. But we don't have the landing phase, right? Because all the lights are behind us, we can't see it now. So we get cut off about 30 seconds earlier. But overall, we see if you have overlapping fields of view of our distributed cameras in San Francisco, this will give you a backup navigation solution for your aircraft just in case something goes wrong. It would be ideal to maintain communication between like your ground-based solution and your airborne solution to get you more confidence in your state estimation as you want to ensure safe landings. Okay, and then we'll look at our last paper. So here we flew the Alta 8 quadcopter at NASA Armstrong Flight Research Center. Now, due to limited budget, we don't have money to buy landing lights, so instead we use traffic cones as our visual aids. So here's a Google Earth screenshot of the helipad markings and cones in Google Earth. And then here on the right, this figure shows the world coordinates with the helipad as a center for the origin. And if you want more details about where they are in latitude and longitude, you can check out our papers. So the Alta 8 starts over the helipad facing towards the helipad there in the bottom left. So this resembles like you're starting at the top of a glide slope for a landing, and then the Alta 8 manually flies down towards helipad, eventually reach the bottom, and then you land. Unfortunately, we don't have a glide slope controller, so we couldn't perfectly follow that suggested glide path angle of 9 degrees. Here's a picture of initial feature detection with Harris corner detection, and it shows a lot of the key features with less of the irrelevant detections. So we're able to see like the helipad sharp corners and the cones. So this is a good method for us to use for our application. So we have fairly accurate position estimation until we land because all the cones and helipad markings are behind us. So that's why we see drift and divergence at the end. As we get composite measurements, they kind of come in and out, the drift kind of goes up or down, and that leads to fluctuations. And we see a similar story for velocity. Overall, our orientation estimation is pretty good. There are some fluctuations because we don't get consistent composite measurements. We also compared the PIXOC, the flight controller of the drone, with the GPS telemetry data as ground truth against OrbSlam 2, which is a vision SLAM algorithm, and then our valve system. So OrbSlam 2 kind of matches well at the end, but then our valve system matches everywhere else generally because we lose features at the end during landing, and that's why it diverges at the end there. Okay, so when we have composite measurements, the overall accuracy is slightly worse than GPS because we have some gaps in between available measurements. But there's a major difference when we don't have these measurements, orders of magnitude. So ultimately, if we can get consistent composite measurements, then you can get more accurate state estimation, and this will help reduce that drift and fluctuations. Here's a table of how fast each of these processes take. So the EKF runs the fastest in milliseconds, composite takes centiseconds, and then the feature detection corresponds methods. This takes the longest time, about a second, so it's the limiting factor. So for real-time implementation, we need this to run a lot quicker. So for conclusion, so composite, as we say, you need at least 4 detected coplanar points so you can get some good detections and good results. You also want to maintain communication between your ground-based and airborne navigation solutions if possible. This will increase your confidence in your state estimation, and that'll help ensure a safe approach and landing. We also want to make sure that you obtain accurate state estimations so you can get higher accuracy for approach and landing for advanced air mobility. And then finally, we've demonstrated a potential alternative position navigation and timing solution for AM aircraft in GPS-denied environments. Here are some references you can check out for later. And thank you for listening. Any questions?
Yeah, that was very interesting. Thank you. We got a question. Could you use the sensors on the runway and the aircraft for synchronized landing?
Yeah, that's the traditional method. They have like the PLASI, or there's another acronym I'm forgetting. There's like VASI and something else. They have like angles on the runway, and then they show different colors. So I think like white is you're on the glide slope. If it's red, then you're too low or something. And if it's like blinking white, then you're too high. So they use those for traditional approach landing at runways. Yeah.
Awesome. While we're waiting for any last minute questions, how much do you think something like this would cost to implement?
Well, that's a good question. I don't know. So I ran this on my regular NASA laptop. And so if you have a really strong and fast computer that can do like the feature detection and correspondence in real time, that might be the most expensive thing. And then you just need a generally pretty good camera. I don't know the exact cost for that, but I'm assuming less than $10,000, maybe, but I don't know for sure. I never really
Awesome.
looked into those numbers.
Yeah, fair. Well, thank you. I appreciate it. It was very interesting. And okay, we got one last one. Do you know what the break-even point is between composite and GPS-based navigation accuracy?
I believe GPS you can typically get like sub-meter or meter accuracy. For composite, if we always get a good measurement consistently, so like we don't have any big gaps, then we can usually beat GPS. The problem is if we don't see 4 coplanar points, then we're going to get a gap. And then that's when we start drifting and getting divergence. So that's really the main challenge there.
Got it. Awesome. Thank you so much. I appreciate it.
Yeah, thank you.
Thank you again for everyone for tuning in. Now I'm just going to go over how to leverage NASA technology for any of your ideas. Let me just share my screen. Great. Yeah, thank you again, everyone, for tuning in. So just wanted to quickly go over how to use the technologies that were presented here for your company, your group, whatever it might be. So the NASA Technology Transfer Program has 10 different programs at the, or it has, it's all one program, but it's located at 10 different centers throughout the United States. And here are the centers. We are at NASA Ames Research Center, and our kind of core competencies are intelligent and adaptive systems, reentry systems, advanced computing and IT, aerosciences, things like cost-effective space missions, biology and astrobiology, space and earth science, as well as climate science. So that's what we kind of specialize in here. And every center has their own specialties and will have their own technologies that come out of that. So since its inception over 50 years ago, the NASA Technology Transfer Program ensures the innovations developed for exploration and discovery are broadly available to the public, maximizing the benefit. So whether you start a company and takes products or create a new product line, you can gain a competitive advantage in the marketplace by putting NASA technology to work for you. So this means by reducing time to market, vetting proven tech, etc. So the question always is, why should a company license NASA technology? A NASA license allows you to allows access to a technology for testing and to implement it into a system, service, or product that can result in sales. The Ames Technology Transfer Office cares about success of commercial businesses, and negotiation of licensing terms is done by a case-by-case basis. So I just want to touch on some success stories. The one on the left here is de-icing that is used now for railway lines. So if you ever see somebody out here spraying something on railway lines, that's to make sure that the trains can run in cold weather. And the one on the right is a cool little thing. So it's a mineral analyzer, which was used on the Mars Curiosity rover. And what it did was it would take in situ soil from the Martian from Mars and take it, put it in a little vial, shake it up very quickly, and use X-rays to see what the X-ray spectra of that was. So yeah, sorry about that, everyone. So yeah, the one on the left is the anti-icing formula that I was talking about that you'll see, workers put on rail lines for trains to run in colder weather. And the one on the right is the in situ soil analyzer. So what it does is it takes samples wherever you are, puts them in a small capsule, shakes it really quickly, and shoots X-rays at it. And through that, you can see the X-ray spectra and analyze what type of soil it is. So rather than taking it back to the lab, you can just do it where you're analyzing the soil. So now I'm just going to go through how to look for the technologies and then license the technologies. So the best way is to go to technology.nasa.gov, and you can do a search for the technology using descriptive keywords, or you can simply click on the NASA patent portfolio. So that's the way we'll be going through this presentation. So once you click on the NASA patent portfolio, you'll see that we have 15 different categories that have licensable technologies. So we have such a wide array of technologies, and you saw that today during the presentation. So we have things from communication, medicine, biotech, optics, robotics, instrumentation, aerospace, you name it. And so let's explore the instrumentation category. So once you click on the instrumentation button, you'll be greeted with different technologies from all across the NASA agency. And here's one that's at a NASA Ames real-time radiation monitoring using nanotechnology. So once you click on that, you'll be greeted with a TOPS page. So it's a technology overview preview page. And what this does is it gives you an overview of the technology, what the technology is, and the benefits, as well as the patent number and then applications. If you have any questions, you can click on the questions button, and that will go to our agency concierge, who can help direct your questions to the right NASA Field Center. And if you want to download the fact sheet to kind of give it to other people, it's just an overview of what you saw on the webpage. So an overview of the technology, the benefits, the technology itself, the applications, and any publications. And so it's very important to, if the technology has a patent granted already, is to click on the patent link and read the patent. Just make sure that the numbers match up with the patent number that you clicked on. And it's very important to review the patent claims and the description of the technology, because that's what you're basically going to be licensing. So you got to make sure that the technology meets the needs that you have. So there's also more resources on how to license the technology. So you can go under resources and how to license, and that will show you, the step-by-step process of what it'll look like for licensing a NASA technology. And then if you're interested in any technology, every technology overview preview page has a apply to license button. And just wanted to point out that your company must be legally formed in the United States in order to apply for a license. So after you click on the apply for license, you'll need to create a guest account in our Atlas system, which is our automated technology licensing application system. And once your account is created, the license application page should open. The first step is selecting a license type. And here are the different types of license types. So we have 3 license types. We have our evaluation one, which is kind of like a test drive. So this option allows you a short-term permission to explore the potential of a technology and to learn if it will fit your business development goals. Then you have a startup license. So this is offering up a no upfront cost commercial use for patented technologies. I do just want to mention on the evaluation license that you can't commercialize it. It is just a way to kind of test run the technology. But if you are interested after evaluating technology, then you can do a commercial license, which is a standard commercial license for companies and all these require a business plan, understanding that you understand the technology, how you're going to be using it, and things like that. So the last few questions on the first section, you'll see kind of here below, is will determine your license type. So rather, would it be a startup, evaluation, commercial? And before you advance to the next section, check the bottom of the page to confirm that your intended license type is listed. And it's important to complete the application with as much detail as possible. And you click on submit on the last page, and to be sure to complete the Adobe e-signature process. Once you've e-signed the PDF correctly, your application is submitted, and you will receive a confirmation email that your application has been submitted. And finally, I just wanted to touch on our NASA software catalog. So this is free software that people can use. It's available at software.nasa.gov. And our open source software is available at code.nasa.gov. There are a few open source softwares on software.nasa.gov, but most of it will be on code.nasa.gov. There are different release types. So you have a government purpose release type. That's if you have a government contract. And then you have your general purpose one. So that's if you're in the US, if you're in the US and in other countries, US and foreign, and if you're just in the general public. Just as a reminder, all but open source software require a software use agreement and apply for it for free online. Here are just some quick resources that you can use. So we have our technology transfer program overview at technology.nasa.gov, our NASA patents, our free software, success stories. So those are kind of the things I touched on, like the de-icing, and then NASA Home and City is kind of like a virtual way of looking at that. And feel free to reach out to myself or Kim Hines, the office chief at arc-techtransfer@mail.nasa.gov if you have any more questions. And just as a final question for everyone here, what is left undone in your company group that you might search in NASA technology for a solution? So thank you everyone for tuning in. That concludes our webinar, and we look forward to hearing from you. Thank you.